Dear students, let us discuss this question now. A ball is thrown downward, okay. Ball is thrown downward with some velocity greater than the terminal speed in a viscous liquid, okay. Dear students, we have a viscous liquid here, right? We have a viscous liquid here. Now a ball is thrown with some velocity, it is moving downwards with some velocity, and that velocity is actually greater than the terminal velocity. Now inside the liquid, some forces will act on the spherical ball, and what are those? One would be the buoyant force, that would be equal to volume into density of liquid into acceleration due to gravity, okay, V rho g. This would be buoyant force, dear students. Rho is the density of liquid, okay, and obviously viscous force will act in the upward direction, Stokes force, which is 6 pi eta r v, okay, right. Now one more force, weight will act vertically downwards, okay, weight would act vertically downwards, right. Now dear students, terminal velocity is the maximum constant velocity, or not maximum, terminal velocity, yes, actually when the ball is thrown or ball is just dropped, then terminal velocity is the maximum constant velocity attained by a spherical object while moving through a viscous medium. And when velocity is actually equal to terminal velocity, then dear students, these two forces, what are those? Upthrust, okay, plus this Stokes force together balance the weight, and assuming the density of ball to be sigma, together balance the weight, right. Now when you throw an object with a velocity greater than terminal velocity, then obviously this v rho g plus 6 pi eta r v, if this is terminal velocity, okay, vt is terminal velocity, okay. When object is moving with terminal velocity, then these two forces, actually upthrust and Stokes force, balance the weight. But if velocity is greater than the terminal velocity, dear students, then these two forces will be greater than the weight, okay. So this spherical ball will experience a net force in the upward direction, so it will retard, okay. It is moving, it is thrown in the downward direction, but net force is in the upward direction because the upward force is greater than the weight, right. So ball will retard, its velocity will decrease, okay, its velocity will decrease, dear students, right, till it becomes equal to terminal velocity, right, dear students, right. Okay, so velocity will decrease, not increase, okay. So velocity will not increase, B option would be more appropriate. It will not exactly be a linear curve, okay. It will be a little curved graph, right. B is going to be the right answer for us, okay. Option 2 is going to be the right answer for us. Dear students, let us discuss this question now. A liquid having coefficient of viscosity 0.02 decapoise. Dear students, decapoise or poisuli is SI unit. So value of coefficient of viscosity is 0.02 poisuli, okay. I'm not sure that spelling is right, must be right only. Eta is 0.02 poisuli. Okay, poisuli is the SI unit. 1 decapoise is actually 1 poisuli, and poisuli is SI unit, right? Is filled in a container of cross-sectional area. So area is 20 meters square. True. If the viscous drag between two adjacent layers, the force is 1 Newton, right? Then the velocity gradient is. Dear students, if these are the successive layers of liquid, right, then we know the formula. If this is dx, this velocity is v, this is something greater than v, this is something less than v. Okay, distance between the successive layers is dx. Then each layer opposes the motion of the other with a force equals to, just writing the magnitude, obviously this force is negative, indicating that it opposes the motion, eta a dv by dx. Force is given, eta is given, a is given. We are asked to find the value of dv by dx, velocity gradient. I have not used the negative sign, I'm just finding the magnitude. Okay. So force is 1 Newton, eta is 0.02, dear students. Area is 20 multiplied by definitely the velocity gradient. Okay. True. Right. Now dv by dx here would be, okay, let me make simple calculations here. This is 2 divided by 100, dear students, into 20 equals multiplied by dv by dx. Okay. Now this is actually 100 divided by 40 equals to dv by dx. So value of velocity gradient dv by dx would be 2.5. Okay. And unit would be meter per second every second. Okay, every meter per second per meter. So net unit would be per second. Okay, so this is 2.5 per second. Option 2 is going to be the right answer for us, dear students. Dear students, let us discuss this question now. The angle of contact does not depend on. Okay. Dear students, the angle of contact depends on the surface tension. Okay, depends on. They are asking does not depend on. I know that it depends on surface tension. Okay, and surface tension in turn, this in turn depends on soluble impurities present in the liquid, because when you add detergent to the water, its surface tension decreases. Okay. Surface tension depends on soluble impurities. It also depends on temperature. Okay. So they are asking does not depend on. So angle of contact actually depends on surface tension, dear students, and surface tension depends on temperature. So this cannot be the answer. And obviously surface tension depends on soluble impurity. So this cannot be the answer. Okay. Cohesive force. See, dear students, let us understand this thing. How the angle of contact or shape of liquid meniscus is decided, right? Let us take the example of water and glass. In case of water and glass, adhesive force, this is a glass tube, right? This is a molecule of glass and this is a molecule of water. This is another molecule of water. Okay. Now adhesive force between water and glass molecules greater than the cohesive force between two water molecules. Okay. Now this is the weight of the molecule. Okay. Now you know that in this way the net force on the water molecule at the end would be this Fa minus Fc, adhesive force minus cohesive force, minus mg, and this would be the net force. Okay. Now liquid molecules will arrange themselves in such a way that they become perpendicular to the net force. Now in this case liquid's meniscus would be concave. Okay. And therefore this would be the angle of contact. Okay, angle of contact is the angle which tangent to the liquid surface makes with the walls of the container. So we can clearly see that the angle of contact is dependent on the cohesive or adhesive force, right? And also obviously we have got the answer. It is dependent on the cohesive force. So it is not dependent on the inclination of the surface in contact. However, I'll explain what happens in case of mercury and glass. Okay, in case of mercury and glass, I'll quickly explain. Right, dear students. So if this is mercury and glass, right? This is a glass molecule, right? Now this is a molecule of mercury. This is another molecule of mercury. Now for mercury, the cohesive force is greater than adhesive force, right? Cohesive force is greater than adhesive force. Mg acts downwards. True. Now the net force here would be cohesive minus adhesive. Okay. Mg will act in the downward direction. Okay. This would be the net force. Right. Now liquid molecules will arrange themselves perpendicular to the net force in order to maintain equilibrium. Okay. So meniscus would be convex and angle of contact would be obtuse. Okay. So clearly you can see that the angle of contact is decided by the cohesive or adhesive forces. So it is only the inclination of the surface in contact which, on which does the angle of contact does not depend. Option 4 is going to be the right answer for us, dear students. Dear students, let us discuss this question now. What will be the work done in increasing the radius of soap bubble from r by 2 to 2r? Okay. Dear students, this work done against the surface tension. If you increase the radius, you have to do some work against surface tension. So work done against surface tension is equal to surface tension multiplied by change in area. Okay, is it the bubble or drop? So it is the bubble. So bubble has two interfaces. So we take the change in area. We take the double of change in area. Okay. So surface tension multiplied by, this would be, dear students, surface tension multiplied by 2 for two interfaces of the bubble. Okay, into area would be final area of bubble minus initial area of bubble. Okay, right, this would be 2s into 16 pi r square minus pi r square. So definitely it is 30 s pi r square. I have taken surface tension to be s. Okay, sorry, they have taken surface tension to be t. Anyways, doesn't matter. Right, so it is 30 pi r square into capital T. I have taken surface tension to be s. They have mentioned that surface tension was actually capital T. That doesn't matter, right? Dear students, let us discuss this question now. Two soap bubbles of radii 2 cm and 4 cm. So this is a soap bubble, dear students. Radii R1. Value of R1 is 2 cm. Okay. There is another soap bubble now. Okay, there is another soap bubble, dear students. And radius R2. Value of R2 is 4 cm. Right. Now they join to form a double bubble in air. They combine. Okay, then the radius of curvature of interface is, okay, so when the radius of curvature of the interface we are asked, now dear students, you know that the excess pressure inside the smaller bubble would be, what is excess pressure? The difference between the internal pressure and atmospheric pressure. Okay, formula for bubble is 4s by r1. Okay, now excess pressure inside the other bubble would be, delta P2 would be 4s by r2. Okay, if the other double bubble is formed, right, and the pressure, excess pressure inside that bubble, let it be 4s by r. Okay, then smaller bubble, the pressure of smaller bubble will be greater, so the pressure difference delta P1 minus delta P2 equals to, dear students, delta P. Right, now let us substitute these values using the single marker now. 4s by r1 minus 4s by r2 equals to 4s by r. Okay, so this is r2 minus r1 divided by r1 r2 equals to 1 by r. So dear student, in this way we got the formula for radius r1 r2 divided by r2 minus r1. Okay, what is value of r? r1 is 2, r2 is 4 divided by 4 minus 2. So here r would be 4 centimeter, dear students. Okay, so the radius of interface, radius of curvature of interface is 4 centimeter. Option 3 is going to be the right answer for us. Dear students, let us discuss this question now. An ideal liquid of density rho is flowing through a uniform horizontal tube OPQ, horizontal tube, okay, right, with cross-sectional area A with uniform speed V as shown in the figure. The magnitude of force exerted by the liquid on the tube is, okay. Dear students, let us first understand for this tube, okay. If liquid is flowing with some velocity here, right? Okay, right. Now, let us consider this portion. This is delta L. Now, you know that force is equal to rate of change of momentum. True. Since liquid is coming out with velocity v, so here dear students, this was average force, this is instantaneous force. Momentum is mass times velocity. Okay, since velocity is constant, so v is taken out and we'll take derivative of mass here. Now what is mass? Now mass here is actually derivative of volume into density. True. Now what is volume then? Volume is actually area into length, okay, into density. This is the length, okay. You can take this length or delta L, whatever, right. Now area and rho are constant, assuming liquid to be incompressible, okay. Now derivative of length would be again velocity. So this would be rho a velocity square, dear students, okay. Rho a velocity square, right. Now, okay, dear students, kindly note down. Now, if you have a tube like this, right, if you have a tube like this, obviously it is a horizontal tube, not a vertical tube, it is kept on the table, okay, and let this angle be theta, this angle is again theta, okay. Now net force can be calculated using the parallelogram law vector, which is under root f square plus 2f into cos theta, rather cos of 2 theta, okay. So this would be under root of 2f square 1 plus cos 2 theta. Now using the basic trigonometry, now value of f is what? F is rho a v square, okay, true. When it is rho a v square is when the liquid jet strikes a wall, does not rebound, okay. This is rho a v square, okay, right. Now 1 plus cos 2 theta is actually 2 times cos square theta. Now net force can be calculated in this way, okay. 2f square, this would be 2 times cos square theta, this would be 2 times f cos theta. F was rho a v square, that we have already told you. Theta here is 2 theta was 60 degrees as per the question. 2 theta was 60 degrees. So theta here would be 30 degrees, right? This would be cos 30 degrees, okay. Cos 30 degrees root 3 by 2. So the answer is root 3a rho a v square, okay. This was one method to solve. There are many methods for solving this question. Okay, option 3 is going to be the right answer, but I wanted you to retain this formula for net force exerted. Okay, theta, the 2 theta angle may be anything. Okay, it may be 90 degrees, it may be 180 degrees, whatever. Okay, dear students, kindly note down. Dear students, let us discuss this question. Let's see what does the question say here. Okay, a bent tube is lowered into a water stream as shown in figure. The velocity of the stream relative to the tube, okay, is equal to 5 meter per second. So this velocity is given as 5 meter per second. The closed upper end of the tube is located at a height h naught above the water surface, okay, 25 centimeter. It has a small orifice. To what height h will the water jet spurt, water jet rise? Okay, dear student, this is a wonderful question, and definitely we'll be using Bernoulli's theorem for solving this question. Let us see how we will apply the Bernoulli's theorem. So basically the thought process behind the question is that I am going to use Bernoulli's theorem between these 2 points. One point, this is, let it be point 1, and just point outside, let this be point 2. So I'll be using Bernoulli's theorem between point 1 and 2, which says that the sum of pressure plus potential energy per unit volume and kinetic energy per unit volume always remains constant. And by applying this Bernoulli's theorem, I'll calculate the velocity with which the liquid emerges out from end 2. Okay, then you know that v square minus u square is equal to 2as. Can be easily applied, or it is just a projectile, simple vertical motion. We'll use the equation of motion to calculate to what height this water jet will rise. So let us try to solve this question. The step 1 would be drawing the diagram again. Okay, let us solve this question stepwise, because this question is going to explain many things to us, right? So let us do it stepwise. In the step 1, dear students, I'll be happy in drawing the diagram again. Okay, right? So this is the water surface, dear students, and okay, this is a closed end. This is the closed end, and right, this is the pipe, right, again, and it had some orifice here, right? It had some orifice here, right? Anyways, now liquid is flowing through the pipe, okay, and it emerges as a jet, right? It emerges out with velocity v2 and it enters here with velocity v1, dear students, right? Now we are given with something, we are not given the height of the horizontal tube below the free surface of the liquid, and I'm not going to ignore it anyway. Let us assume that height to be h, mean height of the horizontal tube to be h below the water surface. You call it height or you call it depth, okay, right? And h naught is given, it is the height of the orifice below the free surface of the liquid, height in centimeters, one thing to understand, okay, one thing to note. Now we'll apply the Bernoulli's theorem between a point 1 which is just outside the tube here and point 2 which is just outside the tube here, right? Now let us apply Bernoulli's theorem, okay. Now according to this would be, you know, step 2 of the question, okay, this would be step 2, applying Bernoulli's theorem. Now according to Bernoulli's theorem, dear students, according to Bernoulli's theorem, you know that, okay, dear students, the height to which the jet will rise is given as h. So let us assume this height as h dash, okay, so that we don't get mixed with the variables, right? Now for point 1, pressure at point 1 plus potential energy per unit volume plus kinetic energy per unit volume at point 1 must be equal to pressure at point 2, you know where is point 2, plus potential energy per unit volume at point 2 plus kinetic energy per unit volume for point 2. Indeed. Now let us write these values. So pressure at point 1 is h dash height below the free surface of the liquid. So pressure would be P naught plus pressure due to h dash height of liquid column rho g h dash, okay. Now potential energy per unit volume, dear students, for finding the potential energy we must mention a reference level. I'll consider this water surface to be the reference level, so height h dash has to be taken as negative, okay. So potential energy per unit volume here would be rho g, and I'm taking the height as negative minus h dash, right? Now this is half rho v1 square. What is pressure at 2? Point 2 is in the air, so pressure would be atmospheric pressure plus rho g, okay. What is the height? Height above the water surface is h naught, okay, plus half rho v2 square. Dear students, this v2 has to be calculated here, okay. Now let us simplify this thing, okay. Rho g h dash and rho g h dash are going to die, p naught and p naught will get cancelled here, right? And this equation now becomes what? This equation now becomes 1 upon 2 rho v1 square equals to, dear students, rho g h naught, right, plus half rho v2 square. So now considering that density of water is not going to change, I'll cancel rho from everywhere. Okay. Now this will become v1. What is v1, dear students? v1 is actually, as per the question, it is 5. Let us substitute the values. v1 square is actually 5 square by 2. Taking g as 10. Height h naught is 25 centimeter. It has to be converted into SI unit, that is meter. So which would be 1 by 4 meter plus indeed v2 square by 2. Right. Kindly note down, dear students, I'm going to erase this now. Right. I'm going to erase step 2. Okay, because we need the diagram. Right. Let us check. v1 was 5, v1 square by 2 is equal to g into h naught plus v2 square by 2 indeed. Now, dear student, this becomes 25 by 2. This becomes 25 by 2 is equal to definitely 5 by 2, okay, plus v2 square by 2. Now this would become 20 is equal to v2 square, okay, true. Now v2 is equal to root 20. This was step 2 of the question, dear students. Now this is the velocity with which the liquid jet will emerge out from this end 2, from this orifice. Now while moving with this velocity, it will reach some height before coming to rest, and they are asking about the height to which this jet will actually rise, okay. Now for step 3, we will be using the equations of motion, okay, dear students. Now we have initial velocity as v2 and, okay, let me write this initial velocity as v2, and somewhere this final velocity will become 0 when it will rise to the maximum height, okay, true. Now let us use the equations of motion. V final square minus V initial square equals to 2as. Now what is V final? V final is 0, dear students, right? Now what is V1 then? Actually initial velocity is V2. Initial velocity is V2, which is root 20 square, okay. Acceleration is acceleration due to gravity, which is acting in downward direction, so we will take minus 10 into height is taken as h as per the question, okay. So 20 is equal to 20h, dear students, and definitely we got the value of height as 1 meter. So in this case, water jet will emerge to the height of 1 meter above this orifice. Option 4 is chosen as the right answer, dear students. Kindly note down. It was a wonderful question which explained many concepts. How do we apply Bernoulli's theorem? And sometimes when some portion of the pipe is below the water surface, how its potential energy per unit volume is calculated. After that, how do we apply equations of motion for a water jet? Okay. Dear students, let us discuss this question now. The height of mercury in the barometer tube is 70 centimeter due to entrapped air in it, as shown in the figure. Now from this position, tube is pulled up slightly, then the length of mercury column in the tube will be. Dear students, this is a very good question. How do we interpret it? So this is a trough containing mercury, right? Okay. Now this is a tube, which is, sealed at the top, right? Now this is the level of mercury, water surface level of mercury, okay, and they have said that level of mercury is 70 centimeter initially above the water surface. This is 7070. This portion is not perfect vacuum. This must be there must be an entrapped air. They have mentioned that there is some entrapped air. Now dear students, at this point you have atmospheric pressure, okay, and also let this be point A. Now at point B would have pressure due to the air column plus pressure due to 70 centimeter of mercury column plus 70, or you can write as pressure due to 70 centimeter of mercury column, okay, right? Now dear students, you know that since A and B both points are at same level, so pressure at A and B must be equal for liquid to be in equilibrium of rest, okay. So in this way we can conclude that pressure at A equals to, definitely it was equal to pressure at B, and it was equal to pressure of air plus mercury column, and it is also equal to the atmospheric pressure. So here atmospheric pressure is equal to pressure exerted by the air column plus pressure exerted by plus pressure of 70 centimeter of mercury column. True. Now what they are saying, let us understand this thing. They are saying that we have pulled the tube upwards, okay. Now we have pulled the tube upwards, right? So what will happen in this case? Now if you have pulled the tube slightly upwards, in that case dear students, the volume of air would increase, the air column would increase in size, okay. Volume, this is point A, right, and again this is point B. Now here volume of air will increase, Dear student, I'll assume that temperature remains constant. Is it given or I have to assume it? Okay, we have to assume it. If temperature is constant, since they have not mentioned that there is some source of heat which would increase the temperature, so I'll assume that temperature remains constant here. If temperature is constant, then pressure into volume is constant. This is what we call Boyle's law. So pressure would be inversely proportional to volume. Now when volume of air column is increasing because we are pulling the tube upwards, then pressure exerted by air column should decrease. True now, this is true. So again, there is some x centimeter of mercury column, right? Now you know that at point A, dear students, at point A, we have atmospheric pressure, okay, and pressure at A and B must be equal for equilibrium. True. Pressure at point A is equal to atmospheric pressure. Pressure at A must be equal to B, right? Now pressure at A is equal to atmospheric pressure. Pressure at B is equal to pressure due to air. Let it be P dash now because it is little decreased, plus pressure due to mercury. Pressure due to x centimeter of mercury, right? Now dear student, one important thing to understand is that pressure, atmospheric pressure remains same. Atmospheric pressure is the sum of pressure exerted by air column plus 70 centimeter of mercury. Now when this value decreases, when we are pulling the tube upwards, pressure exerted by the air column decreases, okay, this is P dash. Pressure exerted by air column decreases, and left hand side atmospheric pressure remains same, this term decreases. So this pressure exerted by mercury column should increase in order to maintain the pressure at B equal to atmospheric pressure. So mercury level would rise, okay, level of mercury would be slightly greater than or greater than 70 centimeter. Slightly more than 70 centimeter is the answer. Option 2 is going to be the right answer for us. Dear students, let us discuss this question. Two equal drops, okay, two equal drops are falling through the air with a steady velocity of 5 centimeter per second. Okay, I'm not going to change the unit here. If two drops coalesce to combined, then the new terminal velocity will be. Dear students, here actually we know that the formula for terminal velocity is 2 by 9 r square g sigma minus rho divided by eta. Symbols having their usual meaning. R is the radius, g is acceleration due to gravity, sigma is the density of the object which is falling in the viscous medium, rho is the density of the medium, and eta is coefficient of viscosity of the medium, right? Now I can clearly see if we are not changing the other parameters, like we are not changing acceleration due to gravity, sigma, rho and eta, then I can conclude that terminal velocity is directly proportional to square of the radius of the drop. Now two drops actually combine to form a bigger drop. Now two drops actually combine to form a bigger drop. So 2 times 4 by 3 pi r cube equals to 4 by 3 pi r cube. True now. Okay, now this 4 by 3 pi and 4 by 3 pi is gone. So this becomes capital R equals to, dear students, 2 to the power 1 by 3 times small r. Now terminal velocity initially divided by terminal velocity finally is equal to radius square of the smaller drop divided by radius square of the bigger drop. So this is radius square this is 2 to the power 1 by 3. Okay, then new terminal velocity will be, okay, initial terminal velocity was, dear students, 5 centimeter per second. Okay, we are asked to find the final terminal velocity, which is 2 to the power 1 by 3 r whole square. Okay, so final terminal velocity here comes out to be 2 to the power 2 by 3 into 5, which can also be written as 4 to the power 1 by 3 multiplied by 5 centimeter per second clearly, dear students, right? So 5 multiplied by 4 to the power 1 by 3 centimeter per second is going to be the right answer. Option 1 is going to be the right answer for us. Dear students, let us discuss this question now. A vessel contains a liquid, okay, and vessel has a constant acceleration of 19.6. Okay, dear students, so right, this is a vessel, dear students. Now this vessel is moving with some acceleration a. Okay, now you know that in this case the shape of liquid will become like this, right? Now if you take any liquid molecule here, right, now this ma pseudo force will act in the backward direction, mg would act vertically downwards. Okay, right, now what they are saying that it is moving with 19.6 meter per second square acceleration along the horizontal direction. The free surface of water gets sloped with the horizontal at an angle of. So dear students, we are asked with this angle theta, this is also theta. Okay, if this is the perpendicular, this is 90 minus theta, this is again theta. Okay, now if I make a parallelogram here, this is ma pseudo force, this is mg acting vertically downwards, dear students, right? Now this is theta. Now I can clearly see that tan theta equals to ma divided by mg, right? Now m gets cancelled here, so here tan theta equals to a by g, here tan theta equals to, dear students, a divided by g, right? Now a was actually 19.6. Since a is 19.6, so I'll write g as 9.8 only in order to keep the calculations easy. So tan theta here is 2. Dear students, do we have an option here? No, we don't have an option. Don't get confused with this. Tan theta is equal to 1 by 2 because they are asking the angle with the horizontal only, not with the vertical. Okay, now use the triangle technique. Tan theta equals to perpendicular by base, dear students. So I'll assume this perpendicular to be 2, base to be 1, and hypotenuse would be 2 square plus 1 square, which is 5. This is theta. So I can get this sine theta as perpendicular divided by hypotenuse. Okay, So clearly we got the answer. Theta as dear students, theta is equal to sine inverse 2 by root 5. Okay, so it was an easy question, dear students, with very good options. Okay, so option 4 is going to be the right answer for us.